Have you ever wanted to be a data detective? Someone who can look at a pile of clues and figure out what's really going on? Well, that's exactly what we're going to do today. And don't worry, forget the complex math for a minute. Just think of hypothesis testing as our official detective's handbook. It's how we put a claim on trial to see if the evidence actually stacks up. So let's grab our magnifying glass and open the case file.
So here's our first case. It lands on our desk with a thud. A well-known fact states that the average age of college students in a city is 23. But is it? Is that really true? Or is something else going on? This is the mystery we've been hired to solve. And look, this isn't just some random question. This exact kind of thinking is how scientists test new drugs, how companies figure out if their new app design is working. It's all about using data to make decisions you can stand behind.
All right, every good investigation needs suspects, right? Two competing stories, two versions of the truth. In statistics, our suspects aren't people, they're ideas. And it's our job to figure out which story the evidence points to.
But hold on, before we put our suspects in the interrogation room, let's get one thing straight. What even is a hypothesis? It's way simpler than it sounds. It's just a claim, a statement about a big group that we think might be true. For our case, the claim is about the average age of all college students. That's it.
Okay, time for the lineup. First up, meet the null hypothesis. We call it O for short. This is the old guard, the status quo, the official story that says, yep, the average age is 23. Nothing to see here, folks. But then, stepping out of the shadows is the alternative hypothesis, or HA. This is the challenger, the new theory that's making waves saying, hang on, I think you're wrong. I think the average age is actually something different.
Now, here's the absolute most important rule of the entire investigation. We have to treat the null hypothesis, the old story, as innocent until proven guilty. We start by assuming it's true. It's our default setting. Our whole job is to see if we can gather enough compelling evidence to convince everyone that it's time to change their minds.
So the null is always the business as usual story. The no change, no difference, everything is fine theory. And a little inside tip for you detectives, you can always spot the null because it's the one with the equal sign. It's the fortress we're trying to breach. Our whole mission is to find evidence against this one idea.
So, we've got our suspects. Now what? Well, we need an angle, a specific line of inquiry. And the way we frame our new theory, that alternative hypothesis, tells us exactly where we need to point our investigation. One option is to cast a really wide net. That's a two-tail test. This is what we use when we're just curious if the average age is different from 23 in any way. We don't have a hunch if it's higher or lower. We're just looking for any sign that the number isn't 23 anymore. We're looking for clues in both directions. But what if we have a specific tip? Maybe we have a hunch that the average age is actually younger now. That's when we use a left-tail test. We're no longer looking everywhere. All of our investigative resources are now focused in one direction, finding evidence of a decrease. And you've probably already figured out the third option. The right-tail test is for when our theory is that the average age has actually gone up. Again, a super focused investigation. We're only looking for evidence of an increase, and we're ignoring everything else. So, let's nail this down, because it's the key takeaway here. The question you're asking, your alternative hypothesis, is your compass. It sets the entire direction for your test. That little not equal to, less than, or greater than symbol, that tells you exactly where to look. Okay, we have our suspects and we have our angle, but what's the standard of proof? How much evidence do we need before we can make an accusation? In a courtroom, it's beyond a reasonable doubt. Well, in statistics, we have our own version, and we have to set that standard before we even look at the first clue. We call this standard the significance level, or alpha. And here's what it really is. It's our risk level. It's the chance we're willing to take of making a huge mistake. The mistake of rejecting the status quo, of convicting our innocent suspect, when it was actually true all along. Now, the most common alpha you'll see out in the wild is 0.05. That means we're willing to accept a 5% risk of being wrong. But this all depends on the stakes. If you're testing which ad gets more clicks, a 5% risk is fine. But if you're testing a new pacemaker, you'd want that risk to be way, way lower, like 1% or even less, because the cost of being wrong is massive. So what alpha really does is draw a line in the sand for us. We call this the rejection region.
Think of it like a tripwire. If the evidence we collect is so unusual, so extreme, that it crosses that line, bam, the alarm goes off. That's when we know we have enough to reject the null hypothesis.
And this is it, the moment of truth. We've got the suspects, we've got the angle, we've set the standard of proof. It's time to bring it all home and see how a data detective makes that final call and delivers the verdict.
The whole process is actually a very logical path. First, you state your two competing stories. Then, you decide on your risk level. After that, you go get your evidence, your data, and you crunch it all down into one single powerful number called a test statistic. This number basically summarizes all your evidence. Then, the big moment. Does that number cross your line in the sand? And based on that, you make your final call.
Now, when it comes time to speak, we have to be incredibly precise. The language here is critical. There are only two possible verdicts. If your evidence was strong enough, you say, we reject the null hypothesis. If it wasn't, you have to say, we fail to reject the null hypothesis.
Now, did you catch the wording there? We never say we accept the null hypothesis. Why? Because not having enough evidence to convict someone doesn't prove they're innocent, right? It just means you didn't have enough evidence for a conviction. Statistics is exactly the same. We never deal in absolute proof, only in the weight of the evidence.
So here's how that translates into your final report. If you reject the null, you can write, we have sufficient evidence to support the new theory. Awesome. But if you don't reject it, you have to write, we do not have sufficient evidence to support the new theory. We're not saying the new idea is wrong, just that this particular investigation didn't turn up the goods.
Which really brings this whole thing full circle, doesn't it? If we can't ever be 100% sure about anything, how do we make any decisions at all? Well, that's the real magic of hypothesis testing. It's not about finding some kind of absolute cosmic truth. It's about giving us a consistent, reliable framework for making smart decisions when we're faced with uncertainty. It's how we know when the evidence is finally strong enough to challenge the status quo and maybe, just maybe, discover something new.